And there have been several questions that have recurred more than once when thinking about fractures. Several of you have asked, when do we call it a fracture? When do we call it a fault? How do we recognize that in the field? And so we're going to start stepping into faults and fault systems. For the next segment of the class, you have a general description of faults and fault systems in Chapter 8 of your text, and then there are specific chapters sort of interspersed around. If you look as an example, once we start faults and fault systems, we will look at normal faults, which are going to be extensional regimes, Chapter 17. We will look at thrust faults, that's contractional regimes. Chapter 16, we will look at strike-slip systems, and that's going to be Chapter 18 in your book. So we'll be jumping around a little bit, looking at faults and fault systems. The easiest way to determine whether you're looking at a fracture or a fault is that you want to see visible offset of some marker that you have relatively good confidence in. And so if we had a system, let's say we take a field trip, we have a look at a layer of sediments coming across. Here we are in the field pondering. We'll put a hat on. We don't have any arms. There. We're pondering this and we see a system that looks like that. Would you consider that to be a fault, or would you consider that to be fractures?
Fractures.
Fractures. Why? Well,
because it's not separated that.
Yes, no separation, no offset. You have a continuous layer across, and you're not seeing any visible offset in that particular system. However, if we were to go to another outcrop and we saw this, where we're standing here looking, put our hat on, is that a fault, or is that a fracture system? It's a fault because we have visible offset of a known stratigraphic system, layers within that. We can use the basic principles to look at cross-cutting relationships, and we've used initial continuity and say that this is a fault in that system. Now, for a quick review, when we think about trying to classify faults, we tend to classify faults in terms of the type of displacement of the two blocks. And so we want to review some basic physical geology, go back to Dr. Cornell's class. And we want to define some simple relationships. If we have a system here that shows exactly the offset that I drew here, this particular system, we can talk about this being a dip-slip fault to begin with, because most of the displacement that we're seeing, we'd have to verify it, but most of the displacement that we're seeing is in the dip direction. This is what type of fault? Is this a thrust fault, a normal fault, a strike-slip fault, a triple reverse funnel fault?
Symbol fault.
Normal.
Yeah.
Normal? Okay, so we're going to call this a normal fault. And what we're going to say about a normal fault is that the block here that is above the fault plane itself, we're going to call this the hanging wall. Because it is perched above the fault plane itself. The hanging wall will move downward. And that movement downward is relative to what we're going to call the foot wall. So our relative displacement is like so. The foot wall is the wall beneath the fault plane. Now, when we're dealing with this type, let me finish this. What we're imagining here is that if I took this block and picked it up, we have a slope so that the block is resting above. It might be easier if we think about having a very low angle fault like this. This is the block above the fault plane. From this perspective, this is the block beneath the fault plane. So in a normal fault, the hanging wall moves downward relative to the foot wall of the fault. If we go just the opposite, so let's draw a fault similar to this. In this case, relatively, which way did the hanging wall move relative to the foot wall? Up. So this side has moved up, this side has moved relatively down. We're always plotting relative displacement. This we're going to call a reverse fault. Hanging wall has moved upward relative to the foot wall. Does that make sense? When we're looking at normal faults, we generally consider them to be relatively high angle faults, at least at the surface or near the surface, and we can identify a hanging wall moving down. In a reverse fault, again, we consider these to be relatively high angle. Dips on reverse faults may be 60, 70 degree dip on the fault plane, and the reverse fault, the hanging wall moves up relative to the foot wall. Now notice that I have not put any scale on here other than some indication that this might be a stratigraphic layer. We see these faults at almost all scales. We can go to certain areas where we can see a reverse fault where the entire structure is only about that big. Or we can go to areas where we have a reverse fault where the entire structure may be 50 kilometers long. The vertical displacement may be on the order of 10 to 15,000 meters of vertical displacement in the system. We can go to places with normal faults where we find just these little bitty small faults, or we can go to places where the vertical displacement may be as much as 8 kilometers or 10 kilometers, and where the length of the fault body itself is on the order of hundreds of kilometers. So these diagrams are simplistic. We need to investigate each of these in depth because we're going to find out that what we learned in physical geology, we always draw these stick straight faults. And that's not reality. These systems will curve. We find out that in these types of systems, we always draw them as if they were infinite, and they're not. They are finite, they are bounded. There are areas where the displacement on the fault will go to 0. And that kind of is a mind blower to see that we have a fault, and we'll talk about this in detail in probably 2-3 days, that in thrust faults you can have areas of the fault system where the displacement may be 100, 200 kilometers. And then you're going to find other areas where the displacement goes to 0. And so you have this weird dichotomy of how much displacement we can accumulate on a fault state.
Okay, so just to be sure, for a reverse fault, the hanging wall and footwall move in the opposite direction.
Hanging wall moves up relative to the footwall.
Okay.
Then the normal fault, the hanging wall moves down relative to the footwall. And so in physical geology, was there another hand up, another question? Okay. In physical geology, we learned terminology. You learned normal faults, reverse fault, thrust fault, and a thrust fault. Typically in a physical geology class, a thrust fault is drawn again as a kind of a stick diagram where we have a low angle fault and we offset on that low angle fault where again the hanging wall still moves up. So the hanging wall displacement is the same between a reverse fault and a thrust fault. The only difference is the angle of the fault plane itself. And typically in physical geology you explain it that the fault plane here dips around 30 degrees on average. It may get more shallow. There are thrust fault systems that I can take you to where the thrust fault has a dip of 0. And you can also find systems where the thrust fault has a dip of 60 to 70 degrees in that particular system. But in general, in the most simplistic sense, normal, reverse, thrust, and then we have strike slip. Now, did you cover strike slip in physical? Of course. When we look at strike slip faults, what we tend to do is switch away from this type of a cross-section depiction into a system where we're looking at a map view. So we're looking down on a system. In strike slip faults, you generally draw a fault here as a straight line. It is considered to be a vertical fault coming in and out of the board here. And if we have an offset, we have something like this. This would be a strike slip system. Is there a way of further discriminating the types of displacements that we see here? Well, we're going to give it a term. We're going to call this particular system a right lateral strike slip fault. Why did we call it a right lateral? Well, the easiest way to think about it is if you stand on this side. So we're going to stand on this block and look across. This side appears to have moved to the right relative to our position. If we step across the fault and look, that block appears to have moved to the right. So the displacement here is like so, a right lateral strike slip fault. The other way to imagine it, let's say that your grandmother makes the world's best chocolate chip cookies. You get home from school every day and you go to grandma's house to have chocolate chip cookies and milk, of course. So what happens if there's a right lateral displacement? So you go home, you walk down the road, and what do you have to do to get to grandma's house? You have to turn to the right because grandma's house has been shifted to the right relative to where you were before. So you go there, you eat 2-3 dozen chocolate chip cookies, 3 dozen, no, and then you come home. And what do you have to do? You have to turn to the right again to find that connection. So this is a right lateral strike slip fault. If we look at the opposite sense of displacement here, again, we're dealing with a map view. what are we gonna call this?
Strike.
Yes, of course. So that we have here a left lateral strike slip fault. So in this case, this one has moved that way, this one, oops, this one has, yes, this one has moved that way. So we come up here, this block appears to have moved to the left. If we step across the fault, come over here, that block appears to have moved to the left. So we have right and left lateral strike slip faults. Now these are simplistic. These are astonishingly simplified. And what we're going to do over the next several days is we're going to investigate what we can learn about these as systems, a little bit about how they might develop in natural settings, and we're going to work a little bit on how do we recognize them in the field. Tim?
Stop me if we're going to get into this eventually, but like you said, these are simplified versions. What if, maybe there's some three-dimensional offset? If it's intermediate, how do we determine which one it's more like?
What we're going to find is that when we describe the systems, this is a perfect question. What we're going to do is we're going to describe them based on the dominant offset. Since these faults are occurring on a planet that is spherical, the surface is curved, that means that all of these faults are going to show some sense of curvature, and all of these faults are going to show a mixture of offsets. And so a lot of times what you will see is a normal fault that shows a little bit of strike slip, or a reverse fault that shows a little bit of strike slip. And so we will start looking at terms like, well, this is a transtensional system dominated by normal faults, but the oblique component is X. We will start looking at how these different offsets can mix and then try to recognize the geometry of the overall offset in the system. Okay? The other thing to keep in mind is that when we look at this, these are drawn as being independent of scale. When we get into larger systems, a lot of times we have to use remote imagery, large-scale mapping exercises where you're mapping over 5, 6, 7, 8, 10 square kilometers during a mapping exercise, and so you don't see this perfect relationship a lot of times. It's a story that you have to piece together. So, perfect question. Now, what I would like to do is to click through some of the slides just to kind of get an overview of the types of systems we're going to be looking at. Then we're going to step into normal faults, normal fault systems. We're going to end up in Africa to look at the rift systems. We'll look at some of the large-scale rift systems that we have in the western U.S. We will look at reverse faults, thrust fault systems, strike slip systems, and then we're going to say, okay, there are cases where we can have a normal fault that gets reactivated and becomes a thrust fault. So we're going to look at inversion systems where we reactivate faults with a different sense of displacement. And we'll find out that there are cases where we look at a fault system and say, okay, this is a fault that's all of the above. It's had every type of displacement possible in that system. So they will be a little bit more complex than these very, very simple types of, did it work? Nope, it didn't. But again, okay. So, what I would like to do is just scan through some of these slides. This is on the website. Where is the going? There it is. Okay, so normal fault, we say the hanging wall moves down. when we look at normal fault systems, this will include things like landslides. A landslide is a type of normal fault system. And what we're looking at here, this is the Gros Ventre slide that occurred. I believe this particular system developed in 1925. What had happened is that this exposure here is the tin sleep sandstone, which is a very porous sandstone. It's an Aeolian berg, Aeolian deposit. There had been an extended period of rainfall, had filled up the entire system's porosity with water, and the weight exceeded the strength of the material. So there was a landslide that broke loose here. This is the primary slide, this is the secondary slide, and it came down right toward us. So this defines the fault scarp. This is the debris flow from the fault scarp. It actually created a small dam that dammed a lake. That lake subsequently, or that dam subsequently failed partially. There's still a lake there, but about half the lake drained in a flooding event and killed about 6 people in the town of Kelly downstream. And so this is a modern landslide. Landslides are considered to be part of the normal fault system. Landslides occur worldwide. There have been some recent devastating slides in the Philippines, in Malaysia, in Indonesia, where tens of people have died just because of a landslide. Yeah.
So landslides includes mudslides, right?
Depends on how it starts. If it's a debris flow, no. If it has a definable scarp, yes.
Okay.
And so you have to look at how did it develop, how did the system actually behave down from that system. Here's another landslide event. This is the Slumgullion landslide. This is in Colorado. This is over Slumgullion Pass, and we're on the road down here going to Lake City. This is an enormous landslide. You can see the head wall scarp up in here. This particular landslide is still active. It is moving. Portions of this are moving about 20 meters per year. It actually reached the river, formed a lake, Lake City, and you have, to my astonishment, you have $1 million homes built on top of the landslide. And you can go walk around the area and see, okay, this is the toe of the slide right now. You can see it's actively displacing. You can see displacement of utilities. Yet you talk to the people in the city and they seem to be impervious to the notion that this is an active landslide. In fact, some of the biggest homes were on the barren spots of the landslide where it had been recently the most active. Just astonishing. This thing is enormous in size and is still moving, still displacing. Here's a small scale fault. This is a little bitty normal fault. It is the Amsden fault. Fault plane is dipping about that steep, and we have this side moving down relative to this side. Now that's a simplification because there's some strike slip in here as well. But from what we can see here, this has apparently displaced. Our dip is like so, this displacement is down. We have some odd drag features here related to the strike slip. In fact, this fault may have seen more than one type of displacement as the Bighorn Mountains have lifted. Here we have microfaults. This is the lens cap here that's 65 millimeters in diameter here. So that we're looking here at a system where these individual little microfaults have offset and rotated. So this would be faulting at the micro scale in this particular system. Now let's go to faulting at a macro scale. This one is interesting. This area off to our left is Middle Park, Colorado. We're looking at the Gore Canyon entrance here. one of the major railroads cuts through here. This is at what is called Inspiration Point in Gore Canyon. The town of Kremling is off behind us and to our right slightly. Do you see a fault here? Does anyone want to point to a fault?
Is it the one on the far right?
Show us. Well, that's okay. It's all right. if you can do
This
it.
right here.
There is a bit of a fault there, but if we look, what's happening right there? See that sediment dipping? And it's going to run right into granite right there. So the fault, thank you, the fault is in this particular area here. This is up, this is down. Now, is this a massive fault that caused the uplift of this range? We're on the tip of the Gore Range here. Or is this a relatively small scale fault? That's a tough question. Without knowing more about it, you really can't answer that question. What we see is a fault coming through about right there, offsetting this downward relative to the granitic system over here. These rocks are, let's see, this would be a mixture of Paleoproterozoic biotite gneiss and granite in this system. This would be Triassic, it looks like chunk water here. So this is apparently a relatively minor normal fault bounding the edge of Middle Park. Fault plane would be right about there in here. This is down relative to this, but it's a relatively small scale fault. Probably doesn't explain all of the displacements that we see here, because this is up and is up on the order of about 8,000 meters relative to the surrounding basins. Steve?
Where this fault is, I mean, from what it looks like, it slopes down quite a ways past it.
Yeah,
So
right
wouldn't the uplift part be a little bit further down anyways?
The actual fault bounding the uplift is over here,
It's on that side.
all the way at the edge of Gore Canyon. Because what happens, the road that we're driving on here comes up to the steepest part of Gore Canyon, takes a right so you can't really see it. When you get to the town of Kremling and look back, and you see that this is a massive, massive reverse fault over here.
Okay.
Tremendous uplift coming, and I'm not near far enough. I'd have to be in the parking lot over here. Massive reverse fault, and then a minor normal fault on the edge.
So are there several peaks going towards it? There's like that one peak here, and there's not top.
Oh, yes, there are multiple changes as we move over. So this is a huge reverse way over here, and a small normal superimposed on top of the reverse fault. Faults can be difficult to recognize in the field. When my wife and I first stopped here in August, we were both standing there kind of going, this looks odd. What's going on? It took us 2-3 minutes to figure out that, okay, here we have a normal fault in the system. So they can be difficult to recognize in the field. This is a little bit easier. We have switched over. We are now in Utah, near Moab, just north of Moab. There's a great Mexican restaurant in Moab, by the way. We vacation based on restaurants. Now, if you look at this, do you see any faulting?
Yes.
Okay, so are these normal faults? Are these reverse faults?
Seems like there's two of them.
Who wants to try to help me work this out? Tim.
So should I come up or?
Yes, please.
Okay. Well, right off the bat, I see this one.
Uh-huh.
Gosh, I'm trying to see where it line up with. It's either going to be lining up with this one or. Yeah, that would make more sense. So
Okay.
that goes to that. So
So is this, which way is this? Is this
this
down?
is
or up?
this is going down.
Okay.
And then this is going up. So this would be a good example of a normal fault.
Okay, what about over here?
There it appears like this used to be part of this, so that's also a normal fault.
Okay.
Again, a normal fault. Do you mean here? Or-
Yeah.
Okay.
this right there,
Yeah,
right there.
this appears to be offset just a little bit, but that's also a normal fault.
Okay, excellent. And so this is a normal fault system. This is part of the Moab fault zone, which is both normal and strike slip. But this little exposure, and I took this photo from the parking lot of Arches National Park. So this is very, very accessible. This is a normal system. And so if we look at it, it is down, 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 down. Everything, the hanging walls are moving down relative to the foot walls. Even over here, the hanging walls are moving down relative to the foot walls. So beautiful example of relatively small scale normal offsets associated with a much larger fault that is just off to our right here. But a beautiful example of normal faults in this particular system. Now, here we have an intriguing problem. We're out in the field. We recognize that there's a little slope here, an offset of roughly 3 meters. This is offsetting a Permian-aged conglomerate, so it is relatively younger. You have a group. This entire group is PhDs in geology, and we were asked to go find the fault. This is the leader of the field trip. You'll notice everyone here is going the wrong way. The leader, Tim Dennison, is going, look. So we had 25 PhD geologists out there, and every single one of us went the wrong way. So identifying these faults can be challenging in this particular system. And so this is what is thought to be a potentially damaging earthquake-producing fault zone, the Meares Fault in that system. Now, we can have large-scale landslides. So we're going to go to Hawaii. That would be nice. Here we're on the Big Island, Hawaii, and we're looking at the Hole'ipali. This is a normal fault scarp. You're looking here, the displacement on this particular system on the Hole'ipali, you're looking at right at about 500 meters of displacement. This is an active normal fault. And so if we go back, see this right there? This is the Big Island. This is Mauna Loa, Mauna Kea. That scarp right there is what we're looking at in the next slide. So that is the Hole'ipali there. This is an active normal fault scarp. This is moving down and has displaced recently. It displaced and produced a relatively large magnitude earthquake in the 1990s. This is actively going down. Just behind us, we have sea caves and sea cliffs, these enormous sea cliffs, where you're looking at 300-400 meters down to sea level. And every time a wave comes in, this entire system will tremble. It's really cool.
Talk about
Because
wave power.
You're sitting there thinking, you know, okay, wow, is that it? Is that the one? Is this the one? Are we going to go down? It would be intensely exciting for a very brief period of time to be on this when it decides to finally go down. If we look at Hawaii, Hawaii is unique in that you have an enormous accumulation of basalt. In the system, basalt is relatively brittle, not very strong, and so the Hawaiian Islands are actually failing. They're falling apart on these types of normal faults. And if we adventure around in Hawaii, if we go to the other side of the island, this is the Waipahu Valley. It's a beautiful overlook. The road is a fantastic road. You have to have four-wheel drive. And they tell you never stop, because if you stop, you will not get started up again. Even if four-wheel drive, you can't stop on the road and then keep on going. You can. We tried. Do you see a normal fault here? Does anyone want to be adventurous and identify the normal fault? Yeah, you want to do it? You want to point to it? Sure. Where's the normal fault?
I'm thinking kind of like this area
Perfect.
here.
That's exactly right. This is the scarp of a normal fault. The fault developed around 1.5 million years ago. At the time, this is considered to be Kohala time in Hawaii. Early system, about 1/3 of the island at the time disappeared in a massive landslide. And so the remains of this particular scarp, all of the material here are out in oceanic depths. And you can identify the blocks on sonar. So this is an older scarp where the island was unstable 1.5 million years ago and fell apart.
Do you think that's gonna happen again?
Oh, yes.
Soon?
Absolutely. I don't know if it's going to be soon. There's some intriguing things going on. A friend of mine is the chair out at Hawaii Institute of Geophysics, and he's been working on some of the parts of the Big Island, and there's some intriguing things happening along some of these old and more recent poly, indicating that they may be trying to displace again. So the potential is there. I'd say the probability is very, very low, but the potential is there. Now, normal faults, they come in all sizes, all scales. We're in the Tetons. This is the Grand Teton there. Do you see a normal fault? Well, this is a tough one. If we look at this slope right there. It repeats again and 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 again, all the way up the Tetons. It is dipping about that angle. Over on that side, we have basement. Over on this side, we have sediment. If you were to drill down where I'm standing taking these photos, if you were to drill down, you would have to go, in this particular case, 25,000 feet to find this material again. This is a normal fault. This is a large scale normal fault system. Where we are, we've had displacement down where you have about 25,000 feet of vertical displacement on this particular normal fault. So this is a classic example of a crustal scale normal fault, beautiful exposure of the fault plane itself on these slopes. And you can reason out that this has to be a normal fault, not a thrust fault, because of the angle of the fault plane itself and the fact that the hanging wall, which is us here, has moved downward relative to the foot wall over there. Do you see that? Beautiful example of a normal fault in that particular system. Now, if we look at reverse faults, here we have a small scale reverse fault. This is broken back anticline. It's called broken back anticline for a very good reason. This is a difficult area to get into. You have to take your Jeep as far as you can drive a Jeep and be relatively happy that you're not going to turn it over anywhere. And then you have to stop and hike down a cliff face to get into this thing. It's an exciting walk. And you have this beautiful little reverse fault.
Now, I seem to remember, is there a mountain called Brokeback Mountain? Or
There's
is that a
a-
movie?
That's probably a movie.
Okay.
This is called the broken back fault, broken back anticline, which is a little reverse fault, this side coming up relative to that, so displacements are this way. And this is relatively small scale in its offset. If we look around, we get these little pop-ups so that we actually have a little reverse fault coming right through there and another repeat of it there. So this would be a small scale reverse fault in that system. This is a slightly larger reverse fault. This is Williams Canyon Fault. Again, this is just outside of Kremling. I left off the G. This is just outside of Kremling, Colorado. This up here by the cowboy hat is Precambrian basement.
It's near the Kremlin.
XB. This is Cretaceous shale. So we have this enormous, right through these kids' heads, an enormous reverse fault where this has moved upward by approximately 10,000 meters relative to this reverse fault. Very large scale. This is a fantastic place to go. You notice that the students are having a hard time getting up there because it's loose, unconsolidated shale. It takes roughly half an hour to slog your way up to the top because you take 3 steps, lose 2. It takes roughly 25 seconds to get back to the bottom. You simply jump out onto the shale, work your feet, and you ski down. Very, very quickly. Watch out for the barbed wire fence at the bottom. So, beautiful, large-scale reverse fault in this particular setting. We're on another large-scale reverse fault where we're standing, taking the picture of the high bighorns here. We're standing on Pennsylvania sands. And yet, up here, you have granites. The granites up here are some of the oldest basement rocks in the area, about 3 billion years old, 3 gigaounds. And you have a tremendous vertical displacement. We can't see the fault plane. If we had to identify the fault plane, I would be hard pressed. If you haven't walked out there and that's it right there. But without going out there, you cannot recognize that. So these things can be challenging. Now this is Zeisman Dome. There is a reverse fault that cuts up right through, let's see, did I do that right? Oh yeah, right there. Reverse fault that cuts up right through there. But if you don't go put your feet on it, it's hard to recognize. This develops as a fault propagation fold. And the easiest way to think about it, and this will look stupid, but down here is the footwall. This is the hanging wall. What we're going to do is we're going to lock the tip line, our fingers, and then we're going to displace. And we form a fold. So that is how this feature developed. And so the lock point is right there, and it has caused this sort of domal asymmetric anticline to form in that particular system. And so this is part of the Wyoming-Provence system. We're in the Bighorn Basin, which has, oh good grief, there's probably 50, 60 of these sorts of structures along the Bighorns. Small scale faults, we're outside of Canyon City, Colorado. This particular photo was taken, oh my gosh, a long time ago, 1975. This was field camp. You can see these rocks come in and terminate, and so that's a thrust fault, where older rocks have come out over younger rocks. These are Ordovician in age, these are Pennsylvania in age. And so when we walk over there, this is what we see. This is the Fremont Dolomite. This is the Pennsylvania Fountain Formation. Comes up and gets bent over right at the fault plane, right there. So you can see these faults, and we'll finish off here. You can see these faults on all scales. They can be a little bit challenging. Oh, thank you. It decided to log off. These faults can be challenging to identify, and so we need to build the expertise, to build the understanding of how these systems develop, how our knowledge of these systems has changed over time, and where the key questions are today. Because anyone that tells you that they understand faults and fault systems perfectly is fooling themselves. We don't. We know a great deal, but the number of questions that we have far, far exceeds what we know. And so it makes it very exciting to work on it. And it's funny when you go to these huge international conventions and talk to people about fault systems that they're working on, and the first answer they always give is I don't know. I'm not sure. I think this is what's going on, but these are the questions I'm trying to address. So it makes it fun to work with. All right. See you, what's today? Today's Wednesday. See you on Friday. Well, yes, those of you in lab, please remember we're meeting at Red Bud Valley. Be prepared to be muddy a bit. And bring insect repellent, because we had a few ticks last time. Yeah. Yeah, that's fine.